afternoon. My name is Lauren Goyette, and I'm a meteorologist at BOW News. Let's take a look at the forecast for today. It's going to be another hot and humid one with muggy air and highs in the upper 80s, lower 90s, winds in the 12-mile-per-hour range in the southwest direction. There's supposed to be thunderstorms later tonight, so we'll keep a watch on that for sports events later tonight in case there's any cancellations, especially girls Falcon soccer game at 4 o'clock.
Pointed this way. Yep.
Now, why is it important that I shared all this information with you? Well, regardless of your race, your gender, your ethnicity, your social status, the weather is relevant to you. It's relevant in terms of determining what you're going to wear for a particular day or what you're going to do that day. It determines whether you're going to have school tomorrow or a snow day, or if your sports event's going to get canceled that night. And it influences us on a day-to-day basis, but it's also important to be able to accurately forecast large-scale weather events. Things such as hurricanes, tornadoes, snowstorms, droughts, and fires. And all of these things have a much more profound impact on human society. And these have an impact on agriculture, transportation, tourism, energy, the economy, and especially human life and safety. One large-scale weather event could completely destroy an entire season of crops. And not only would this destroy that farmer's particular economic standing, but would also lead to a lack of fresh food in the area and lead to an increasing price of fresh fruits and vegetables in that area as well. Human transportation via cars, trains, and planes is constantly being interrupted by the weather. And it's important that people taking transportation are aware of incoming weather events. So pilots need to be aware if there's going to be thunderstorms so that they don't fly their passengers through a thunderstorm and put them in a potentially dangerous situation. It's important that a driver knows whether there's going to be snow or fog so that they can leave early enough to get to work safely and on time. Tourism is also impacted by the weather because skiing industries constantly need to be aware of how much snow is coming so they're able to determine how much fake snow they need to make. And airline prices are constantly fluctuating depending upon the weather in that particular destination. Energy companies are in a constant need to be aware of impending weather because they need to prepare for additional demands that a weather event might provide them. So communities have a typical energy demand, but a weather event such as a snowstorm might require them to need more heat energy in that particular period of time. So if an energy company isn't prepared to supply that demand, then there could be disastrous effects from, say, blackouts or brownouts, especially during a severe weather threat. The economy is also impacted by the weather, in which the prices of goods is constantly fluctuating depending upon the need for them. So if a company is aware of some sort of impending storm like a hurricane or something, they're able to produce more of a product that might be necessary during that particular storm. And last of all, and most importantly, is human life and safety. So severe weather storms are disastrous to human life, and especially hurricanes, things like that have torrential rains and damaging winds. They're known to kill people very directly and large numbers of people at once. And they can also kill indirectly with, you can see behind him the damage that they cause to properties and lack of food that they create in the area. And tornadoes act in a similar way where they can kill large numbers of people directly, but they can also lead to disastrous effects based on the damage that they leave behind. Droughts are also a huge one. They cause a lack of food in the area, a lack of water. It makes it easier to spread illnesses throughout large communities. So those are also disastrous. And fog and heavy rain are very common in causing accidents. So there's just no shortage of life-threatening, severe storms in our world. And in fact, in the decade of 1950 to 1959, there were only 23 severe weather threats. But between the decade of 2000 and 2010, there were over 350. That's a huge increase, and that translates to a total of 36,000 weather-related deaths just between those 10 years. So it's obviously important that we accurately forecast the weather, but how is this done? So the first part requires there to be observations and measurements taken on the current state of the atmosphere. So this is done with radiosondes attached to weather balloons, it's done with satellites, with radar systems, and human observation especially. And all of these things, all of this information is put together into what's known as data assimilation, and it just creates a large picture of what the current state of the atmosphere looks like. And the second part of this process involves the computing systems that are in the supercomputers in the government. And they contain mathematical models that are nonlinear in nature, so that's an idea I'll talk about in a minute. And It's just a bunch of differential equations, which are pretty much equations that describe how something changes over time. And so that could be your temperature, your humidity, wind speed, all sorts of weather-related variables that change depending on the time. And so they put in the information collected in the first step as what's known as an initial condition, and they evaluate it over some period of time. Could be days, it could be hours, and they're given an accumulation of that change in time as your prediction of what's the temperature going to be like in a few hours, or what's the humidity in a few days. And so that's where they sort of get what their prediction is going to be. And it's important that these are calculated on supercomputers because there's so many countless equations and variables that are involved in this process that if you were to try to do it by hand, the time that it would take you to do the entire thing, it would just be past the point of where you're trying to predict to. So the more accurate the information you collect in the beginning steps, the more accurate your forecast is actually going to be. And the increased accuracy of forecasts can actually also be attributed to increasing computing power as well as increased availability of information about the current conditions. So that comes from weather stations, radar systems, and even like trackers in your smartphones are allowing us to get more information about the current state of the atmosphere. But despite all of these improvements, there are constantly uncertainties in forecasting, and this is due to what's known as chaos theory. And chaos theory was discovered in 1961 by Edward Lorenz when he inputted a small difference in an initial condition when trying to forecast the weather. Now this difference was 1,000th or 10,000th off in the data he was using, and what he got was two very different forecasts. And he learned that small disturbances in data don't actually average out over time, much like what scientists at the time thought, but they actually compound exponentially. And that's due to the nonlinear nature of the models that I discussed earlier. And so he titled this Sensitive Dependence on Initial Conditions. And he created an attractor, which is a set of three differential equations that when combined together and solved, creates a chaotic system, as you can see here, and it's in a three-dimensional plane. It's just showing each of the planes separately. And the system is known as an attractor because you can see it follows, the solution follows around these two specific points. It sort of orbits them, but it never actually hits them. And it continues to follow a similar pattern of behavior, but never crosses itself over again, which is also a behavior that can be seen in the weather, in which similar patterns occur, but can never be seen exactly the same as they were. When a slight difference in initial conditions is inputted, the attractor follows a similar pattern, but with different results. So these are two different attractors. I programmed the one that's on the right. The one on the left was one I found on the internet. But you can see how the different initial conditions created different solutions. And while they look very similar, the differences between them are very large. And so I have, so this is a distance over time graph. So this is calculating the distance between the two graphs over time, and the displacement between the values was 1%. So that's a very small difference between the two initial values. And you can see how in the beginning here, there's not too much change or not too much error at all between the two graphs. And it's sort of a red stable area there. And that area is what we are able to accurately forecast during. That's about 5 to 10 day period where we can pretty accurately forecast the weather. But eventually you can see that the models will break down over time. And that's what happens when we try and forecast, say, past 10 days out. And this discovery contradicted the theories of scientists at the time and led to more detailed observations being made about the current state of the atmosphere. But due to all this uncertainty, we have to be able to quantify how uncertain our forecasts are. And so that's what meteorologists do, and it's called ensemble forecasting. So they do what Edward Lorenz did, and they take their initial conditions and they take very small differences between them. So you can see the temperature values are pretty close together. But you can see when it goes over time, they all change very differently. And so that's your ensemble of forecasts. And meteorologists will compare and they contrast the different forecasts that they have, and they determine which one they think is actually going to happen. So you can see here in the middle on the very right, there's a large number of them that point towards that middle value for that period out in time. And so if a meteorologist were to pick that value, they could say that their forecast is pretty confident. But if they were to pick, say, a top or a bottom value, their forecast isn't as certain. And so that's what I mean when I say they have to quantify the uncertainty of their forecast. So that's what happens when they say 20% chance of rain, 100% chance of rain. They're evaluating how confident they are and what they're telling you. So with all this information about overcoming chaos and improvements made in forecasting, how does this translate to actual numbers? Well, between the years of 1900 and 1989, there were over 216,000 weather-related deaths just per year. But between the years of 1990 and 2010, there were only 34,000. That is a significant decrease per year. And this also translates to the lessening effects of large-scale weather events. So in 1900, the Great Galveston Hurricane killed 8,000 people. To give some perspective, that is the size of the town of Bow. That would be everybody in here dying from one hurricane. So that's a lot of people. Those numbers are unheard of today. And some more current numbers would be Hurricane Harvey killed 68, Hurricane Sandy 127, and Hurricane Irma 134. But something specific about Irma is that they were able to forecast it so well that over 6 million people were able to evacuate before the storm even hit. So that saved a lot of lives. In conclusion, it is obvious to see how important it is that we accurately forecast the weather due to the increasing number of severe weather threats, as well as the numerous aspects of our lives that weather impacts. So whether that be agriculture, transportation, tourism, energy, the economy, and especially human life and safety. So if we want to continue developing our world, we have to do so with accurate weather forecasts. Thank you.